So Rick Cattell wrote a nice paper in 2010 about scalable SQL and NoSQL data stores where he had a taxonomy of these systems and placed popular instances of these systems into that taxonomy. And so this slide corresponds to his grouping where each color is one of the groups that he defined. So he sort of lumped them into key value stores, document stores, and extensible record stores. And so what he meant by that was a document is, an example of this is an XML document or the JSON object that we looked at in the Twitter assignment where you can have sort of arbitrary nesting, and it's also extensible. You can add new things to it whenever you want. Okay, so no top-down schema being enforced. Okay, an extensible record you can think of as much like a database record, except that new attributes can be added. Okay, so there is some notion of a schema that's used for different various purposes, and in particular, there's sort of groups of attributes that are manipulated together, these families. But you can stick new attributes on an individual row, which you're not typically allowed to do with a relational database. And then finally, a key value, I'm using the term object here, is a set of key value pairs. So the difference here is that there's typically not a schema of any kind, so you don't care what keys there are. It could be any keys at all. And there's no exposed nesting. And what I mean by that is, a value can be anything you want. So you might have some kind of complex object in the value, but it's not going to be sort of visible to the system. It's just going to be a blob, a black box object that the system doesn't know anything about. Okay, so sort of only one layer of nesting is aware of the system, unlike a document store or a document object that might have multiple layers of nesting that are exposed to the system. Okay, and so his characterization of NoSQL features, admitting that there's perhaps not a formal definition of well, there certainly isn't a formal definition of NoSQL, but the term tends to be applied in contexts of systems that have these features. So some ability to scale simple operation throughput to many, many servers. And by simple operation here we mean key lookups or maybe even attribute lookups or reads and writes of just one or a few records, right? So these sort of needle in the haystack kind of operations as opposed to these big analytic queries like we've been talking about with MapReduce and with databases. Okay. And second criteria is the ability to replicate and partition data over many servers here. So, break a single large data set into multiple pieces automatically, because you don't have to manage this yourself. And here you might see the term sharding and horizontal partitioning. The difference between the two, if there is any, is not particularly important, so you can think of them as synonyms. Whenever you see sharding, think horizontal partitioning of a database table. You'll see the term horizontal partitioning used more in the database community and sharding used more in the NoSQL community. Okay, and then a simple API, so no query language. This corresponds to the first bullet. These are the simple operations. And then critically, a weaker concurrency model than what I'm saying is ACID transactions now. Now, we'll talk a bit about ACID in the next slide, but I'm not going to go into a lot of detail here. There's 40 years of research on this topic, too much to cover in this course, especially when we're mostly focused on reading data and analyzing data as opposed to a concurrency control. But we will spend some time on some techniques of concurrency control in a minute. Okay. And then some efficient use of distributed. He talked about efficient use of distributed indexes and RAM for data storage. So this is kind of minimizing latency is their emphasis as opposed to just throughput. All right. And then typically they have this ability to add new attributes to data records in various ways, as we talked about on the previous slide, right? So the lack of no schema is what you can think of here. All right, so this is no schema, no transactions, and we'll go into more detail there. No query language, with no SQL, right? And high scale. Okay. So ACID, and he talks about this term base that never quite caught on. I wouldn't typically use this term, and I'm not sure I recommend you do either. Certainly ACID is much more permanent in the vernacular than this base is. It's okay. So ACID is an acronym standing for these four concepts: atomicity, consistency, isolation, and durability. And just briefly, this is the context here is when we're modifying records in, let's say, a database. And we can be modifying lots of different records across different tables, anything we want. And the point is, they're all lumped into one transaction. And so each one of these refers to, that's the context we're in for each one of these concepts. So atomicity means that the entire transaction either needs to succeed or it needs to fail. Right? You aren't allowed to have partial transactions succeed. Consistency is the slipperiest one in my mind, and this quote down here maybe captures that. So it's sort of any data written to the database must be valid according to all defined rules. And the question is, well, where do these defined rules come from? Sometimes they're actually integrity constraints in the database. Other times they're just sort of business logic rules, perhaps enforced by the application or just assumed by the application. And so it's a little bit difficult to, say, prove a system achieves application level consistency. But that's the goal. The point is, if there's only certain allowed states of the database to have, you should not have a system that allows transactions to put you into an invalid state. Okay, you should only be able to go from working state to working state. Isolation means that while the transaction is occurring, other readers and writers can't sniff partially completed values. Okay, partially you can't sniff values of data items before the transaction is complete. They only get final states, and this one is the one most often relaxed in various ways, in part because it's very expensive and also because it's not usually all that critical. And then durability just means that if you report back that the transaction succeeded, it needs to have actually succeeded, meaning it needs to be written out to some kind of non-volatile storage so that if the power goes out and the machine crashes, you don't say, hey, whoops, that transaction I accepted yesterday or committed yesterday, well, you need to do that again because it didn't take. All right, so that's not allowed. So fine. So these all make some sense with a little bit of slippery notion of consistency, as I mentioned. And then the pun here is they tried to sort of force an acronym on base, and this isn't Rick Cattell. This came from elsewhere. But the idea is, well, it's basically available. There's some notion of soft state, and it's eventually consistent. And we talked about eventual consistency, at least an overview in the previous segment. Fine, that's all I'm going to say about that. So something else I like about this paper is he sort of says, look, the major impact systems here are these three: this Memcached or Memcached, Dynamo from Amazon, and Bigtable from Google. And the reason he says these are the major impacts is you can kind of trace the lineage and show that other systems are basically taking ideas from one of these three early systems. So Memcached is very, very simple, and we'll talk a little bit about one particular technique that it made popular in a minute. But it's essentially just, hey, look, let's load everything into memory, scale it out across many, many machines, right? And then we'll be able to serve read requests without having to go sort of query the database. We'll just be able to do it directly from memory. And what's also made this very, very popular is you can kind of install it on top of your either scale out or non-scale out database, and it sort of just works, right? It just makes things faster for read heavy workloads, and that was kind of a nice thing. So that's an older system, sort of on the scale of 2003, but it's still very widely used and very, very popular, and there's been all sorts of extensions to it, and so we'll talk about perhaps the most basic version. Amazon's Dynamo paper, which has been somewhat more recently released as a cloud service called DynamoDB. What they did was they didn't invent the concept of eventual consistency, but they did sort of show that if you relax the consistency notion, that will allow you to scale way, way out. Okay, and so data fetch are not guaranteed to be up to date, but updates are guaranteed to be eventually propagated everywhere they need to be. And we gave an example of why this was a good idea in the last segment. And then Google's Bigtable, that we'll spend some time on, demonstrated that record-oriented storages could scale to thousands and thousands of machines, and that was something that databases had not shown. Okay. So let's talk about each one of these systems in turn. So Memcached, as we said, is a main memory caching service, no persistence. The basic version is no replication, meaning that there's only one copy of every cached value. So if something goes down, if that goes down, then it's gone. That's okay because it's sort of a cache. It's not assumed to be the golden copy of anything. Okay. That being said, there's been many extensions that provide these various features, including membrane and membase. So this is a pretty mature system and still in wide use. And an important concept that they adopted in this context was consistent hashing. And so I want to explain a little bit about what consistent hashing is. So that's one takeaway from this lecture. Okay. So first, just for those of you without necessarily having too much of a background in programming, what is hashing? So what is regular hashing? Well, the problem we're looking at here in this hashing is a very, very general concept, very fundamental to all of programming. But in the context of what we're doing here, we're trying to assign data keys to a bunch of different servers. Okay. And the simplest way you might do this is sort of a round robin thing, right? The first key goes to the first server, the second key goes to the second server, and you keep going until you run out of servers and you start back over at the first one. And that's implemented by this modulus function. Okay, so each of these data keys is placed somewhere on one of these servers at various points. Fine, that's how hashing works. What's wrong with that? Well, what happens if I want to add more servers to the mix, right? I want to scale out I want to double the number of servers. Well, every existing data key now needs to be reevaluated, its location needs to be reevaluated by computing k mod 2n instead of k mod n, which means every single data item is going to be remapped at once. So every time you want to add a server, you end up having to move all the data that's already in the system, and you're dead in the water. Okay. So what you want is some notion of consistent hashing, where consistent means when I place something somewhere and I add more servers, it's typically going to stay right where it is. And so there's a pretty good trick that's pretty simple to understand for doing this. Okay. So here's how it works. The first key idea is you're going to map the server IDs into the same space as the key values themselves. Okay. So we apply a function that I'm going to leave sort of unspecified and map server 1 to some point on this circle, and server 2 some point on this circle, and server 3 someplace on this circle. And now what that does is divide this space up into 3 sections. Okay. And now each key that comes around, I also map it into this circle. So this gets key 1, and this gets key 2, key 3, key 4, key 5, key 6, key 7, and so on. Okay. And now this entire region, server 1, server 2, server 3, this entire region is responsible for all of these data keys. Sorry, this server is responsible for all these data keys. And then this server is responsible for all the data keys in this region. And this server is responsible for all the data keys in this region. Okay. And so what's nice about this is now when I add a new server, server ID equals 4, well, let's say it comes around and it gets stuck right here. Well, that's a bad spot for it for my example, actually. Let's say it comes around right here. Well, you just apply the same rule. It should be responsible for every key in this region, which means that these two guys need to be moved from server 3 to server 4. Right? But you only have to move that one section of data. And so it splits at most sort of k over n data items. All right, so this is a nice trick. And there's all kinds of extensions for supporting replicas when you need to put data items in more than one place. Well, you just sort of hash it to 2 different places. So if you want to hash the same data item to 2 different places, compute h of, let's say d is the data key, and then also put it to put it in all 3 places, and you're done. Okay. Okay, so how do we serve requests in this setup? Well, imagine the key space is divided across various servers in the same way we described, and a request comes into the leader that may be elected among the servers, or may just be assigned top-down by the system, or could even be assigned randomly. And the naive way of doing this is, well, this server would check to see whether it has the key being requested, and if it doesn't, it would just forward the request on to the next guy. Okay, but this is no good because there could be many servers, and this would incur sort of a latency every time you want to do a read. So a better way of doing this is for each server to memorize the locations of other servers in the ring, and which servers it memorizes is like this. So it knows where itself is. It knows A plus 2, A plus 4, A plus 8, A plus 16, and so on. And what it does is it knows the key range being managed by each one of these servers. Okay. And so what it can do is forward the request to the server that is closest to the key range it's looking for. Okay. And so this takes a logarithmic number of hops away. You know, imagine there's lots of servers here. And keeping all this information straight when new servers come in is still, you know, each server only has to keep track of a logarithmic number of servers as well. So everything sort of ends up being logarithmic to maintain this. Okay.